All right, now that we've laid the foundation of probabilities, permutations, combinations from our probabilities bootcamp, especially how to count the number of ways events can occur, let's apply those ideas now to one of the most famous and most counterintuitive problems in probability, the birthday paradox. Here's the puzzle. How many people need to be in a room before the probability that at least two of them share a birthday exceeds 50%? Most people guess 100 or more, but the actual answer is 23 people. We'll show you later how this is computed, don't worry. Now, that's not only unintuitive, it's a perfect example of why combinatorics matters because the number of possible pairs grows much faster than the number of people. When there are n people in a room, the number of possible pairs is n times n minus 1 over 2, as we have demonstrated before in our combinatorics video. Remember our placeholder approach and dividing by the placeholder factorial for uncounting? Kindly revisit that video if you're not sure what I mean by that. Now for 23 people, that's 253 possible pairs, or 253 chances for a match, rather than the 23 people that we have in mind that we compare with 365 days in a year. That's why the probability skyrockets so quickly. The key insight is we don't count birthdays, we count pairs of people. But even with combinatorics, computing the exact probability directly is actually quite messy. So instead of calculating the probability that at least one pair matches, we compute its complement. We'll take a look at the probability that no one shares a birthday. Then after that, we get 1 minus that probability to get the complement, again, that the probability that there's at least one pair that shares a birthday. Focusing on the problem, if everyone has a unique birthday, then the first person has 365 choices out of 365, and any day is fine. So we plug that in, our first placeholder. The second must avoid the first person's birthday, so that gives him 364 over 365. And then the third person must avoid the first two, so that becomes 363 all over 365, up to the nth person. Now, the probability that all birthdays are unique is probability of 365 over 365 times 364 over 365 and multiply until you get 365 minus n plus 1 all over 365. Now, to get the probability of that complement, then we simply get 1 minus probability of that, and that's the probability of a shared birthday among n number of people. Now, for n equals 23, the probability comes out to about 50.7%. Okay, let's generalize this so we can put formulas in a spreadsheet like any good data scientist is fond of doing. Then we generalize the approach and compute other probabilities. For the problem of getting no shared birthdays, the numerator turns out to be the permute formula or the permutation formula in Excel. 365 taken n at a time, as we show here. The denominator is just 365 raised to the power n, where n is the number of people we are testing as input to get probabilities. And this is where Excel and our previous math lessons help, and we will review them in detail below. What are our Excel steps? First, we create our input cell for n, the number of people. Then let's create the combin formula showing how many people are taken two at a time to show how many pairings there are. Then we compute permute 365 by n for the numerator. Then we compute 365 raised to the power n for the denominator. Then we get the probability of no shared birthdays as numerator divided by denominator. Then finally, we get the complement 1 minus that probability to find out the chances of people sharing a birthday with n people around. And as we show here, it works out to around n equals 23, where the probability is more than 50%, there will be at least a pair who share a birthday. Now let's extend the analysis and create a data table. It's important that your formulas are dynamic, that everything updates when you change the number of people, or otherwise the data table will not work. So first we create a column starting from 5, 10, 15, 20, all the way up to 60, like here. Then we put the reference, the output table in the target cell just above the column we want to populate. Then we select by highlighting the data table, go to menu, data, what if analysis, data table, column input cell, and reference the input for number of people, and then run it. You'll see the values grow rapidly. Around 23 people will give you 50% probability, around 40 people gives you 89% probability, and around 50 people just gives you about 97% probability. So what if we wanted 95% probability that there's a shared birthday? It turns out to be n equal to 47 people. We have a 95% chance of a shared birthday. Even perhaps surprisingly, with just 60 people, you're almost 100% guaranteed to have a shared birthday among them. It does not look intuitive because we're thinking of 60 people sharing 365 days, rather than the 1,770 pairings that 60 people create. In closing, so we've used combinatorics to count the number of possible pairs, probabilities to compute complementary events, and our placeholder approach to plug in numbers for the computations. And we use Excel's data table to automate the search for a target probability. This combination of theory plus computations plus a spreadsheet is a powerful way we'll use again and again in data science, finance, and statistics. If you found this video helpful, kindly like and subscribe to support the channel. See you next time!